So the question is about like what is actual command. So actually in many of the existing demos, there can be a person providing high-level commands to the robot. For example, which direction should the robots like walk? Should the robots like rotate in place or just still like keep walking forwards? Conditioned on that high-level actions provided by human, the robot has to decide this kind of low-level actions. The low-level actions are typically, for example, the joint torque that applies to each and every one of the joints on top of these robots. So that is how like this typically like looks like, meaning humans give high-level commands, condition on high-level commands. The robot has to use this policy to decide this kind of low-level like actions, which is instantiated using like joint torque. So like I mentioned, one biggest lesson I learned from these lines of work on locomotion is that the simulation doesn't have to be perfect. As long as you randomize enough, it can generalize very robustly in the real environment. But such lesson hasn't really been generalized like very well in the manipulation domain. So in the manipulation domain, like how accurate the simulation needs to be and how much does the sim to real gap matters is still a research question people hope to answer. So I can give you one specific example. If in the simulation, you are pushing a box forwards, if in simulation the box rotates for 10 degrees, but in reality it rotates for 12 degrees, it may not matter that much. But if in the real world, your grasping was successful, but in simulation, the object just flies away because of some kind of numerical issues, or if the object like slips like away between your fingers, that's problematic. So there are regions where sim to real gap matter. There are other regions sim to real gap may not matter that much in the manipulation domain. And people still are trying to answer and trying to understand like how sim to real gap can happen and what are some of the most important like recipes and characteristics that this simulation needs to have for the most reliable like sim to real transfer. So if I understand your questions correctly, you're asking like there are still a person like providing high level commands to the robots. So your question is, can the robot come up with better plans than the human? So I can actually give you a more nuanced perspective. Although many of these videos seems very nice, there is a human operators operating the robots to choose which route to go. For example, like what people typically do is, for example, let's say there's some kind of rough terrains or some pile of rocks, and the humans can actually try to command the robot to going forward, trying to climb those kind of rocks. If that fails, humans can actually provide some other high-level commands to get around this pile of rocks. So there can be some kind of learning also on the human side in understanding the capabilities of those robots. So this is also why some of this video can actually looks very nice, because humans select the routes that the human knows can show the limits and also the capabilities of this kind of low-level controllers. And how to do that autonomously is actually a very interesting like questions people are also doing research upon. So then I'm gonna continue. So I've discussed like some of the successful examples and power of reinforcement learning, and I also discussed the limitations of reinforcement learning. And we still haven't really seen very, very successful and wide-scale deployment of reinforcement learning in manipulation yet. And we humans not just learn from trials and error. We actually build this type of internal model. So we're asking the question, can we actually learn the models from the robot's interactions with the environments and using that model for the robot to do better physical interactions? So specifically, what we are touching upon, again, back to this figure, is how we can learn and approximations of the real physical world. And how can this approximated physical world that runs on the virtual domain can help guide the robot's actions and decide what action to take in the real physical world. So let's say if you already have the model, for example, let's say you have already learned the models like we humans have in our like mental like environments, we can predict, given the current state as t and also the action t, how the state of the environment will change into states t plus 1. And then we can use this essentially as a forward model, like given the current state and action predict the next states. So what actually is the problem for us to do the planning, which is essentially an inverse of this forward model, where the plan is to give the current state and the target states, and you come up with the action that can allow the robot to achieve the target states. From a given current state showing the blue dots, we have the targets showing the red. We can have maybe some initial guesses of how the actions might look like. And our model, our approximated learned models, will be able to predict the sequence of the evolutions of the states, which is shown in this green like trajectory. And then we can measure the distance between these green dots and the red dots. and back propagates or doing optimizations using the gradients of their distance, with respect to all the actions along their trajectories to do this type of optimizations in order to know like what actions can guide us to getting us closer to the targets shown in the red. And obviously the model may not be accurate enough. So we typically only execute the first actions and we obtain the new states from the environment. And we can re-optimize the action sequence using gradient descent or any other optimization technique you use to do this trajectory optimizations. And one of the key benefits, especially recently with the development of GPUs and also neural dynamics model, is that you can use the GPU for parallel and simultaneously sampling to allow you to do like a large scale sampling and optimizations of those action sequences, which is actually quite efficient. So like given this like a general framework, you have the model, which is this kind of forward process. And you can always use a kind of forward model to do this inverse optimizations to come up with the actions that can like get you closer to your target configuration. And one of the key questions has always been, what should be the right representation of the environment? What should be the right and most effective state representation is? And how we can learn this model based on this state representation. And over the years, there has been many different investigations on choosing or investigating different type of state representations. Some earlier work including how we can using for them just 2D images as a representation of the states and trying to learn pixel dynamics, meaning how the image might change if you apply a specific actions. This is a work called Deep Visual Foresight, which set up some of the initial works in the whole domains of like word models. And by learning this kind of pixel-based dynamics models, people can come up with strategies that is able to, for example, minimize the distance between the current observations, and some can rotate objects and pushing the objects around in order to achieve the targets shown in green and the current state is shown in red. So this is about like a pixel dynamics. And what people can also do is to use like key points as a representation of the environments to learn like a key points dynamics models. And here, like what we can do is to track the movement of the key points on top of this box over the 3D space, and also learn a dynamics model of those key points as a result of some pushing actions. And then we can allow the robots to use these forward predictive models to plan the robot's behaviors, in order to track some specific trajectories in order to push this box to achieve a target configurations. So besides using key points, so what if you are encountered some objects with even higher degrees of freedoms? So if you go like one level finer, you can also represent those objects using a set of particles, essentially a set of points. Here, like, which is actually a work, that was done when I was here, like, as a postdoc, where we're representing this pile of granular pieces using a bunch of particles and trying to predict how those particles will move around if you apply a specific actions. And this forward model can allow the robots to do this inverse decision makings that handle a wide range of granular objects of different like granular sizes. And we come up with strategies that can gather those pieces into the target region shown in the bottom right like a corner of each like a segment. And the same model with like a good feedback from the environment allows the robots to correct from the model's error and come up with strategies that can be very reliably aggregate all the object pieces into the target region. And obviously, this model not just can generalize to like a different like a granular pieces of different granular sizes. It can also change to different target configurations. Here, you will very quickly realize what the target configurations are. The robot has to come up with a strategy that to do non-trivial redistributions of the granular pieces. And after the redistribution, you have to align the fine-grained details with the target's like shape in order to accomplish this like a pile rearrangement tasks. The task here is actually to rearrange these granular pieces into different letter shapes, all the way from letter A to letter Z. And with this kind of forward models, we'll be very successful in coming up with a sequence of strategies, of course, with feedback from the environments, to allow the robot to rearrange this kind of object pieces into the target regions. And this is actually a highly non-trivial task. And going beyond that, we are also have this like a subsequent work, which I was also involved and done when I was here at Stanford. And we designed this kind of dumpling making robots that is actually equipped the robots with 15 different 3D printed tools, we have 4 RGBD cameras looking at the environment to do a reconstructions of the geometry of this dough. And the robots will have to decide what tool to use and what action to take in order to get this dumpling into, getting this dough into a dumpling. And the key enabling factor is also this forward predictive models represented like using particles. Where here, the red dots are representing the shape of the tool and the blue dots are representing the shape of the objects. The first row is our model's open loop prediction. And second row is like what actually happens in the real environments. So this learned model that directly learns from this real world interactions can very accurately predict the change of the shape of the dough when using different tools applying different actions. And in the end, allows us to have this integrated system that can make a dumpling out of a dough. What's interesting about this video is there's a person constantly perturbing the robots from doing its job. The robots will take the real-time visual feedback from this environment to real-time understanding the shape of the dough, and then using the current observations and also the learned dynamics model that predicts how the environment is going to change, how the dough shape will change if you use a tool to apply a specific actions. And based on this forward model, it is making this inverse decision. This decision is happening at 2 levels, both at the high level, which is to decide what tool to use, which is a task level decision making. And given these tools, the robot is also have to make like a lower level, like a motion level decisions in deciding what specific action to take in order to progress into the next task stage. Humans are just so annoying adding pieces, folding the dough. The robot is very robust to this external disturbance in continuing its progress in doing the task. Here's what's interesting. After the robot cuts a circle, the humans shows no mercy, destroy everything. The robot knows you actually have to start from the very beginning, like redo the task from the beginning in order to progress with this kind of task objective. So this really shows the patience and also the robustness of our systems with this type of external disturbance. And all of these capabilities is enabled by this kind of neural dynamics model that predicts how the shape of the dough will change if you apply a specific actions. In the end, the robots will place the skin on top of this dumpling clip and move this kind of fillings on top of this dumpling skin, and using a hook to close the dumpling clip in order to use this general purpose robots equipped with 15 general purpose tools to make a dumpling out of a dough. So this is about like how we can learn the model and how that model can be useful for downstream like model-based planning. So for this specific case, if we want to describe it more rigorously, we are not using reinforcement learning. We just learn the model and using that model to do planning. Although the plan can be distilled into a policy that can be executed in the real environment in a more efficient manner. But some people also call it model-based reinforcement learning. Decide which background you are coming from. You can either call it like model learning and model-based planning. You can also call it model-based reinforcement learning. But the key idea is you want to learn the model from the robot's physical interactions with the real physical world, and using that learned model that is very effective in helping the robot to decide its behaviors to progress with the task objective. So in this specific case, it is the high-level planning and low-level decision-making is done by 2 different models. So over the high level, we are given the current states, like current observation of the environments and the targets the robot able to achieve. It is essentially a classifier. Classify which tool to use. And conditional on this classified tool label, there's a low level policies that decides what specific action to take in order to progress into the next task stage. Very good question. So back then, this work was done in 2023. At that time, vision language model wasn't very powerful. So at that time, what we did was to allow a human operator to do the data collection and demonstration of the task for 10 times. We use that data to train this kind of classifier to classify what tool to use. That allows us to actually jump back and forth over this chain. Like I mentioned earlier, after the robots cut a circle, the human destroy everything. The robot knows to jump back to some earlier stages, that fits to its current observation in order to do the proper recovery from the external disturbances. So in this specific case, what we have been doing is a combination of sampling-based trajectory optimization versus a policy learning. So what we have been doing is to give the current states of this dough. We have our forward predictive models. We'll be able to sample a bunch of actions and sample a bunch of tools to predict what is the evolutions of the shape of that dough. And then we'll compare the model's prediction with the targets like we hope to achieve, which is similar to what I showed earlier. For example, our model predicts the shape of the dough will go into this green dots, but the target is this red dots. We are comparing their distance. And then that allows us to select the most effective actions that can get us to the target to be as close as possible. And we can do a lot of samples like this. But sampling during the test time is very time consuming. So we do this type of sampling in an offline fashions, which give us a data sets. And we can use that data sets to train our policies that can be inferred at a using a very short period of time to do the inference during the test time. There is still a neural network as a policies. Yeah. Although that policy is learned by distilling from our models predictions over a huge amount of samples. For this specific work, there's no physics-based simulation at all. We actually have a baseline that uses a state-of-the-art deformable object simulator, which is called MPM, material point methods. What we realize is that even if we do very extensive system identification, like estimating the parameters of those physics-based deformable object simulator, the identified model is noticeably less accurate than the model that directly learned from the real-world interactions. Like I showed earlier, for example, the first row is our model's open-loop prediction. The second row is the ground truth. Our model's prediction aligns very well with the ground truth, which is just much more accurate than whatever physics-based simulators out there. Okay, so if there are no more questions, I will continue. So what we have discussed is this kind of model learning and how this learned model can be effective for the downstream like a model-based planning. And the next category of algorithms is imitation learning. So just to recap a little bit, we discussed reinforcement learning. That is directly learning the policies by doing trials and error with the environments, which has a lot of troubles, for example, the sample efficiency, the safety concerns. And for the model learning, what we have been doing is actually force back to the category of supervised learning. We already have the evolutions of the environments. We use that data to do supervised learning, to train this model, and using this model to do model-based planning. And instead of just using supervised learning to train the model, people are also asking, can we do supervised learning also for the policies? This is the general idea of imitation learning, meaning can we have a big data set that shows how a task needs to be done? And using these data sets to train this kind of policies. I'm showing this figure again. This is trying to learn this kind of policy, taking the states as inputs that predict the actions. And all of this kind of learning signals and learning procedures are done through a large-scale collected data from human demoing to the robots how a task needs to be done. So learning from demonstration is, of course, not new. It has been investigated for decades. It's also constantly how we human is actually learning to perform a lot of physical interactions or social activities in the real world, since we are very, very young. So one of the most earlier classic imitation learning algorithms is called behavior cloning. It's essentially trying to learn this kind of mapping. The map currently from this observation O into the action A. And this policy is represented using this function pi parameterized by the theta. So one of the key issues for behavior cloning is called cascading error. Because like I mentioned, the key difference between the robot learning or agent's interaction with the environment is it is a sequential decision-making problem. It differs from a typical supervised learning in the typical computer vision domain in that your error can accumulate and be amplified over time. Let's say at the very beginning, you made a very small error. That small error can lead to a state that is slightly deviates from the distribution of data used to train your model. That will lead the policy to make an even larger error. And this error will be amplified over the temporal horizons that leads to a trajectory that can deviate quite a lot from the demonstration trajectories. So that's the typical issues of behavior cloning. So that's why, oftentimes when people are trying to make imitation learning work, people will follow this type of pipeline, where on the top, we have the demonstration collected by the experts. Then we'll use that as a training data to do supervised learning to train this policy. And we'll roll out the policy in the real environment and observe those failure cases. And we either collect additional data or provide corrective behaviors that allows these data sets to not only contain the initial demonstrations, but also those corrective behaviors that gets the errors from the policies back to the canonical trajectory or get back to the trajectory, they can still successfully accomplish the task. So this is actually a typical like life cycles. We are trying to develop any imitation learning agents or imitation learning algorithms in the real physical world. And along these lines, because like if people do this kind of imitation learning, there's not very explicit definitions of what the task actually is. The task is implicitly hidden within those demonstrations. So there's a class of algorithm called inverse reinforcement learning, where on the left is what people typically like thinking about for reinforcement learning, whereas on the right, where people are trying to use this inverse reinforcement learning to like summarize the rewards from your demonstrations and be able to use that reward to do typical reinforcement learning to learn this kind of algorithms. Some of the earlier like success examples were actually also developed at Stanford by Peter Beal and also Andrew Ng. It allows them to control helicopters to do some very, very crazy behaviors. And this is all actually a very old work. And be able to achieve this type of like agile and effective behaviors on this real physical helicopters is very impressive at that times. So this is the power of learning from demonstrations and using that demonstration to summarize the rewards and in connections with reinforcement learning. This is what we are able to achieve. So obviously over the years, like people have been making the imitation learning algorithms more and more effective, especially in connecting with, for example, energy-based models. So instead of learning this kind of explicit policy shown on the left, they directly do the mapping from the observation O to the actions. People are coming up with the kind of implicit policies that takes the idea from energy-based models that direct taking the observation and actions to predict the score and using this kind of like an energy-based model to do inference to get this kind of predicted actions A has. Allows the robots to handle demonstrations that are very multimodals or handle scenarios where the optimization landscapes may not be very, very smooth. And the robot is able to come up with this kind of strategies, like distill these policies from the demonstrations in doing this kind of content-enriched manipulation tasks. Another to say, like, some of the very recent success of robot learning as a whole is the results of this work called diffusion policy, which again is also taking some of the advances in the community of generative models. For example, this one, like for the implicit behavior cloning, people are drawing inspiration from development of energy-based model. Energy-based model is a type of generative models developed in the deep learning community. And there's another class of like more powerful models in the deep learning community is called diffusion models. And people are also trying to use the diffusion models to use it as a policy function class to allow the agents to also like inherit the benefits and the properties from those diffusion models. So this work was originally done at Columbia. That's where I am right now. And the leads, like a PI of this work now come to Stanford. You can see like many of the work I selected has a lot of like roots like here at Stanford. Like she's currently like at the WE departments at Stanford. And this policy really shows some like a very diverse set of capabilities, allow the robots to do not just like planar pushings, but many like fine grains like manipulation tasks. Not only pick and place, but for example here, spread butter on top of this bread, and also like scrambled eggs, also peeling the potatoes and sliding the books. So it really shows that this type of recipe, where you collect a bunch of demonstrations and using the best policies like learning mechanisms, you can get a policy that works in the real physical world in a very, very efficient manners. Meaning, you collect the data in the morning, you train the policy in the noon, in the afternoon. You can have working policies working in the real physical world. So obviously, there's a lot of caveats in how reliable your policy is and how generalizable your policy is, how diversified the initial configuration can be for the policy to still work very robustly. But still, imitation learning is the most efficient way for you to get a policy that can do something interesting in the real physical world. And for the policies to be very effective and robust to the real world variations, this type of iterative like data collections will need to be in place for the policy to cover those kind of like unexpected behaviors or some kind of deviating behaviors. So this is about imitation learning. So any questions? Okay, so if there's no more questions, I will use the remaining time to discuss some of the recent developments that drive all the craziness about robot learnings, which is like robotic foundation models. And of course, like this is a very involved domain. Actually, for each one of these items, you can actually have a course around them. So like for today's lecture, I'm just like skimming through them very, very quickly. I only tell you the gist, like the high level, like knowledge you need to get by looking at those terms. And for robotic foundation models, it is a type of models that is very similar to like reinforcement learning or imitation learnings in their function class. There's no explicit representation, for example, of the states or this kind of model. For example, this robotic foundation model doesn't learn the model of the environments. It is still a policy that map from the observation and go into the actions. That's still like represented, can be very nicely represented using these figures. So you have this agent, which is a policy, that taking the current state and also the goal as inputs, that is trying to generate these actions that can be executed in the real physical world. But you might say that this is very similar to imitation learning and reinforcement learning. So what's special about these robotic foundation models? So this is actually all rooted back to all the developments within the foundation model domain, especially those language-related foundation model and also those vision language-related foundation models. Meaning it is a policy, but it needs to generalize much better than a policy that just works for one specific task. Like here is actually my definitions. I'm drawing analogies from the current developments of vision language models, meaning their outputs may not always be the perfect one, but to always generate something reasonable as you prompt this kind of foundation model. So what we hope to achieve with this robotic foundation model is the synthesized action may not always be the optimal actions as conditioned by the observation and the task, but the generated trajectory will always be beautiful and reasonable to execute in the real physical world. Like beautiful meaning it shouldn't use any like jiggling motions. It should be smooth and continuous. Reasonable meaning you should listen to the language instructions you are given to the robots. So obviously there are also many different names describing exactly the same things. Some people call it vision language action models like VLAs. Some people call it like a large behavior models. But in the essence, they're all describing the same thing, meaning this policy. Taking the observation and language instructions or whatever like a task specification, is trying to generate the actions that generalize widely across a wide range of scenarios. So this area is actually quite noisy. Noisy meaning it's very, very like hard to quantify the progress of different kind of robotic foundation models. Because you are calling it foundation model, what does that mean? That means you expect this model to generalize like very broadly over a wide range of scenarios. If that's your expectation, you actually need significant evidence to show it actually generalized broadly. So that's why evaluation and quantitative measurements of their progress is very challenging. But still, by looking at their empirical videos, you can still see a lot of very interesting and concrete progress over the past few years. So a lot of the earlier investigations starts like with like RT1, which was released in the December 2022. And since then, I would say maybe roughly every half a year, there's a new model, for example, RT2, RTX, OpenVLA, and some of the recent ones like Pi0 that is making concrete progress along these lines of developing more and more generalizable robotic foundation models. And actually, this year, there's a boost. There's the whole like burst of a lot of like foundation model like Helix, HiRobot, Gemini Robotics, Pi 0.5, etc. So there's a lot of investigations and also investments in this domain in not only like a capital investment, but talent investments in developing better and more generalizable robotic foundation models. So due to the time, I clearly cannot go into the details of all these models. So if you are interested, I actually gave a tutorial 2 months ago at AAAI specifically describing and discussing some of the models along this axis. If you are interested, please go and watch it. And for today, I will mostly give you a high-level overview of what actually is essentials for this kind of foundation models and what it actually looks like with examples from Pi0. So Pi0 was first released in October 2024. I think this is the word that convinced me that this type of robotic foundation model can do some very reliable like dexterous manipulations in the real world environments. It can handle like cloth folding and box folding and many other different types of manipulation tasks at a very reliable manner. And here's how the framework actually looks like on the high level. On the left is data sets. So for any model to be called foundation model, it needs a field for that foundation model, and that field is data. So they aggregate a lot of data, both within academia and also data collected by themselves across many different embodiments where the robot is doing like some kind of interesting and useful task in the real world environments. And they use this data to do pre-training. And one important caveat of this pre-training is this starts with a pre-trained like vision language models. The vision language model that's already trained on vast amount of like a vision language related data that can naturally adapt those kind of semantically like knowledge from those models. And together by doing co-fine tuning, what they call co-fine tuning, using both the objective for action predictions and also the objective adapted from those vision question answering, those type of tasks, you will be able to first preserve the semantic knowledge within those models, but at the same time, you can predict the robot actions. And this is the pre-training stage. A very important like design for many of the existing robotic foundation models is called post-training, which is also inspired by many of the developments in the large language model communities, where you have this base model. Base model can give you some reasonable baseline performance, but you really want the performance to be very, very good on a specific task. You actually have to collect task-specific data to fine-tune the models, do post-training on the data for that specific task, for the performance to be satisfying. So they are evaluating their whole systems over 3 different categories. The first one is to directly using their base model. And their base model can already be good enough for some very simple in-distribution data. The task, is actually the task that might have already been encountered during the pre-training stage. If for in-distribution task, but slightly more complicated, you can do post-training to allow the base model to further improve on those in-distribution tasks. And for unseen tasks, typically you have to do post-trainings by collecting those task-specific data and fine-tune your pre-trained model on these tasks for it to be performance. And this Pi0 model is actually open sourced. And you can just download the checkpoints. My lab, the students in my lab have already been starting to playing with this, their models and trying to do post-training. And we are starting to see some very promising, results. So if you are interested, highly encouraged to try it. That is a very good question. So you are essentially asking about the efficiency of the existing robotic foundation models. So there's a lot of reasons why the policy is actually slower than humans. One of the major reasons is actually adapted from how the data was collected, how the demonstration data was collected. Typically for many of these scenarios, the demonstration data was collected by human, teleoperating the robots on that exact same robots to do the data collections in, for example, folding this box. And human teleoperations is actually slower than human just using their hands to do these tasks, even if you have gone through, for example, hours of training. This is because you are just using a different embodiment than an embodiment that you person is the most familiar with. And also at the same time, because the robot arms are still certain distance away from you, there will be occlusion. Sometimes you have to look very closely, carefully, changing your head, changing the viewing angles in order to really understand, is it the time to progress into the next task stage or not? There's a lot of caveats and inefficiencies of the current data collection regimes. That is why the policy directly trained on those data turn out to be slower than human speeds. So that's why there's a lot of investigations in how we can do those kind of data collections to be even more efficient, to be at human speeds. That is actually a very active research direction. So this is a very good question. So for this box folding task, I would argue this is already a very long horizon task. So I was very impressed by how good this one single policy is able to handle this long horizon task. But you could argue, if you really want this policy to be useful in some a more larger scale, in the wide scenarios, for example, in your home, you not only want the robot to fold the box, you want it to fold the shirts and clean the beds and clean all the messes on the floor. If in those type of scenarios, currently, me personally, I don't believe one gigantic policy is able to adapt to those scenarios. Some higher level abstractions or some kind of scene graph, some symbolic representations needs to be in place as a condition for this vision language action models, for those policies to be the most effective and useful to steer into different type of tasks and scale to larger scale environments and more complicated tasks. So this started with a pre-trained vision language models. So that's why there's already a lot of semantic knowledge that are learned through this large scale pre-training using this vision language data. So that is why some of these generalizations are coming for free, meaning the base model can actually have surprisingly good levels of generalizations at the semantic level. And it's just you have to fine tune this model with those robot data to making sure it can also generalize not at the semantic level, but also at the action level. So we can have the question maybe at the end of, because we are already about time. I still have maybe the last maybe 2-3 minutes. I will discuss some of the remaining challenges, especially along the development of robot learning models. So one of the major challenges the whole community recognize is evaluation. Evaluation currently is primarily done in the real world. For example, this is a picture of Google Robotics. They have a grid of this kind of teleoperating Aloha systems that they are doing data collection and also evaluation. And real world evaluation is both costly and noisy. Their exact words to me was, for evaluation, they have large enough budget such that they can still make progress. This was their exact words. Meaning, if you were to do the evaluation or I were to do the evaluation, the results can be very different from each other, depending on how we specify the initial configuration and how the lighting condition might change. Even the friction parameters of the end effector can make a huge difference in how robust your downstream policy is. So this is very costly, and they have to wait for 2 days for the results to come back. And currently, there's very weak correlation between the training loss and real world success rates. So this is another very important caveat and difference between supervised learning and also this kind of sequential decision making, this kind of policy learning, is for supervised learning, your training loss directly measures how good your model is. But for this kind of policy learning, your training loss measures how good this one-step prediction is, which sometimes may not be, and actually often times, is not indicative of the performance of policy over long task horizons. Even if your loss is low, but for long horizon task execution, your policy can actually be worse. And the training objective versus the task-specific metrics, training versus task horizons, are some of the reasons explaining why it is very hard to come up with even approximate or proxy metrics to measure the performance of the policy. And people have to rely on real-world evaluations. So then the question is, what about doing the evaluation in the simulated environments? There has been a lot of investigation, for example, behavior, which is done in Feifei's lab here, also at Stanford's, and also the Habitat 3.0 from Meta. People are trying to come up with this expensive simulated environments, trying to do evaluation and measurements of the robot policies. And obviously, there has their own issues, especially with regard to sim-to-real gap. How can you do very accurate simulation of rigid body, deformable object, and clothes? They have good correlations with the real-world performance. And assets is also another major issues, where large-scale generalizations and generations of those assets is a huge pain. I can elaborate, but maybe after the lectures. And also how to digitalize the real world is an issue, and how to do procedural generations of realistic and diverse things are all issues of using simulation to do evaluations for robot learning policies. And really, we want to find a correlation between sim and real, and it's calling upon the ImageNet in embodied AI. The reason why ImageNet was successful is because at least for a few years, any progress in ImageNet, meaning progress in deep learning and computer vision, we want the same thing. We won't have this platform, meaning any progress on that benchmark or platform, meaning progress in robot learnings. So that's something that we really want. And I can maybe skip through, we talk about how to build these foundational policies. There can also be investigations on how to build foundational world models. Especially now people are collecting large-scale action condition robot interaction data to train these foundation policies. But there's a lot of dynamics knowledge embedded in those data. If we just use those data to do policy learning, that would be such a waste. So we are also thinking about how we can use this large-scale action condition robot interaction data that was already collected to train those foundational policy, to train these foundational world models and how they can do interplay between each others. And there are some existing works that are thinking about along the direction of building this kind of foundational world models. And there are some very interesting characteristics you might thinking about, do you want it to be 3D? Do you want structural prior? How much learning versus how much physics, and how it can correlate with the real physical world. Maybe actually, I think we are about time, so I will end it here. And this is the future we hope to achieve, to really build this foundational robotic model that can work very widely and generalize very well in the unstructured daily environments around us. And next lectures will be human-centered AI, and that will be the end of today's lecture. Thank you so much.